The icon of the seas is not just a cruise ship. It's a floating city, a moving resort, and one of the most complex machines ever built by human hands. Carrying thousands of guests, towering over skyscrapers, and packed with technology, entertainment, and engineering, this ship didn't simply roll off an assembly line. It was built piece by piece over years by thousands of workers inside one of the world's most advanced shipyards. This is the story of how Icon of the Seas was built, from the very first sheet of steel to its first voyage at sea.
Watch the alignment. All right, hold it.
The pressure readings here look slightly off the baseline.
Let me see. No, that's within the acceptable variance according to the update.
Watch the cables on level 4. Copy that, moving now.
Step 1. Designing a floating city. Long before construction began, the ship existed only as an idea. Naval architects, engineers, and designers spent years modeling every detail using advanced computer simulations. Every deck, every cabin, every pipe, wire, and structural beam. Because a cruise ship isn't just a vessel, it's a hotel, power plant, water treatment facility, and entertainment complex all in one. For Icon of the Seas, engineers had to rethink everything. Stability for record-breaking size, energy efficiency for long voyages, safety systems for thousands of people, and comfort from noise reduction to airflow. Only once every system was digitally tested could physical construction begin.
Ramping up the stabilizers. The forward stress is reaching critical levels.
If we reroute the primary conduit here, the structural integrity of this beam junction improves by 12%.
But what about the power flow stability during peak usage?
If we reroute the main life support system through section gamma,
It improves efficiency by nearly 20%, according to these overlays.
Step 2. Steel cutting and block fabrication. Construction starts with steel, but not in one piece. Tens of thousands of tons of high-strength marine steel are cut using laser and plasma machines with millimeter precision. Instead of building the ship from the bottom up, engineers use block construction. The ship is divided into massive sections called blocks, each weighing hundreds of tons. Inside these blocks, walls are installed. Pipes and cables are pre-fitted. Cabins are partially assembled. This approach saves time and improves quality because workers can build entire sections indoors under controlled conditions.
bring it 5 centimeters to the left. Copy that. Watching the clearance.
Check the alignment on section 4. Looks good, weld it down.
Step 3. Assembling the hull. Once blocks are completed, massive gantry cranes lift them into place inside the dry dock. Each block must align perfectly. Even a few millimeters of error can cause problems later. Welders work around the clock, joining steel plates together until the ship's hull takes shape, layer by layer, deck by deck. Slowly, the outline of a giant cruise ship emerges. At this stage, Icon of the Seas already outweighs most buildings.
We need to inspect this entire strake before handover. All right, I'll start the ultrasound measurements here.
Step 5. Plumbing, electrical, and tech networks. A cruise ship contains hundreds of kilometers of piping and cabling, freshwater systems, wastewater treatment, fire suppression, internet, navigation, security, entertainment. All of it must work flawlessly. Water on board is produced using desalination plants that turn seawater into drinkable water. Wastewater is treated on board to strict environmental standards. Nothing goes overboard untreated.
Check the gauge reading against section 4 on the print.
It's holding steady right at 120, just as expected.
Step 6. Cabins and interiors. While engineers work below deck, interior teams transform steel rooms into luxury spaces. Cabins are installed like building blocks, each one pre-built and slid into place. Restaurants, theaters, lounges, and shopping areas follow. Every surface is designed for durability, fire safety, comfort, and sound control, because thousands of people will live here for weeks at a time. By the time Icon of the Seas reaches this stage, the ship already looks enormous. The steel hull is complete. The engines are in place. Miles of cables and pipes run quietly behind the walls. But now comes the part most people recognize. This is where the ship transforms from a machine into an experience. Because Icon of the Seas isn't just designed to move people across oceans. It's designed to entertain them on a scale never seen before at sea. High above the decks, massive cranes begin lifting some of the most complex structures on the entire ship. Water slides the size of city buildings, multi-level pool systems, surf simulators capable of generating powerful artificial waves, glass observation decks suspended over open water. Each attraction arrives in huge prefabricated sections, carefully hoisted into place with millimeter precision. Nothing here is decorative alone. Everything is engineered. Unlike a land-based water park, nothing on this ship ever stands still. The entire structure is constantly moving, rolling, pitching, vibrating as it travels through changing seas. That makes engineering these attractions a serious challenge. Every slide, pool, and deck must survive 3 relentless forces. First, saltwater corrosion. Salt is one of the most aggressive natural elements on Earth. It eats away at metal, weakens joints, and damages surfaces over time. To fight this, engineers use special marine-grade alloys, protective coatings, and corrosion-resistant fasteners, materials designed to survive years of exposure without failure. Second, constant vibration. Below these attractions, massive engines are running night and day. The ship's propulsion systems generate continuous vibration that travels through the structure. If attractions aren't properly isolated, even small vibrations can loosen bolts, crack welds, or damage equipment over time. So each attraction is mounted using vibration-dampening supports designed to absorb movement without transferring stress to the structure. And third, the motion of the sea itself. This is where things get especially complex. A swimming pool on land is simple. A swimming pool at sea is a moving body of water inside another moving body of water. If not properly designed, waves inside a pool could become dangerous during rough weather. Engineers solve this by carefully shaping pool basins, controlling water depth, and installing internal baffles that limit wave movement. Advanced sensors monitor water levels in real time, allowing systems to automatically adjust when conditions change. Even something as relaxing as a pool requires serious engineering. Surf simulators present another challenge. These systems rely on powerful pumps that push thousands of liters of water every second to create a controlled wave. They must operate smoothly, safely, and consistently despite the ship's motion, changing temperatures, and non-stop use. Behind the scenes, massive mechanical rooms support each attraction. Pumps, filters, control systems, backup power supplies, all hidden from view. Observation decks bring a different kind of challenge. Many feature large glass panels suspended high above the ocean. That glass must withstand wind pressure, temperature changes, and structural flexing, while still giving guests a clear, thrilling view straight down to the sea. Every panel is tested, reinforced, and secured with multiple safety layers. Nothing is left to chance. As installation continues, the upper decks slowly come alive. Bright colors replace raw steel. Handrails, lighting, and safety systems are added. Walkways connect pools, slides, and viewing areas into a seamless experience. But before any guest ever steps on board, everything is tested over and over again. Water systems are run at full capacity. Simulators are pushed beyond normal limits. Emergency shutdowns are